In this video, I'm going to demonstrate how to graph a parabola in the Connect and ALEKS system. So I want to preface this video just by emphasizing that there are multiple perspectives on how to graph a parabola. So we encounter parabolas a lot. Y equals x squared, our basic quadratic parent function, represents a parabola when we graph it. So we can graph a parabola using transformations of that particular equation. We can also graph from what we think of as vertex form, which is another form of the parabolic equation. Our perspective here is based on vertex form, but we're going into a little bit more detail than you may have encountered when you graphed parabolas in the past. So we have a bunch of different attributes for this particular equation that we want to identify. We'll identify all of these and we'll translate them into a graph. So we have an equation representing a parabola given in the standard parabolic form. First, we want to identify the vertex, the value of p, which is a key value indicating the size and the shape of the parabola. We want to identify the focus and also the focal diameter of the parabola. We want to identify the endpoints of the latus rectum. So above and beyond the vertex, the endpoints of the latus rectum will be the other key points that we graph on this particular graph. And then we'll, of course, generate the graph and then write the equations for the directrix and the axis of symmetry. And we want to express our numbers in exact, simplest form, no rounding. So our equation is y plus 3 quantity squared is equal to -8 times the quantity x minus 4. So let's dive in and let's work on these attributes and see if we can get a good graph. Okay, so as with any graphing problem, we're going to do everything on paper first, translating it into a paper graph, a handwritten graph, and then we'll put it in the homework system, not only for the practice, but also so we have something to fall back on if we need to check for mistakes. So first thing I want to identify from my equation is what is the orientation going to be. Now, if you've already worked through graphing ellipses and graphing hyperbolas, in those cases, for those particular graphs, you only have two possible orientations. Either it's vertical or it's horizontal, just based on the kind of symmetry you see for those graphs. With parabolas, we actually have four things we have to consider, or rather four possibilities for what the orientation may look like. So number one, we have to decide, is this going to open horizontally or is it going to open vertically? And then above and beyond that, we have to decide vertically, horizontally, which direction, in the positive direction or in the negative direction. So we're making two determinations that can result of one of four possibilities. So in order to determine our orientation, we're going to focus on which of the variables is squared and which of the variables is linear. So the reason we know this is parabolic versus representing any other type of conic section is because one of the variables is squared and the other one is not. It's linear. So that particular combination is what tells us this is going to represent a parabola. Now, the easiest way to remember orientation is to think about when you graphed parabolas in the past. So for example, if you graphed y equals x squared, the standard quadratic parent function, you know it opens vertically. So anytime your x is squared, think back to that quadratic parent function, the one that opens vertically. Now for our equation, y is squared. So that means rather than opening vertically, we're going to have a graph that opens either to the left or opens to the right. Okay, so we know this is going to be a horizontal parabola rather than a vertical parabola. Now the other determination we need to make is horizontal in which direction, opening to the left or opening to the right. That's going to be based on this constant here that's been factored out of x minus 4. We're focusing on its sign. So the sign in this case is negative. As soon as this sign is negative, it means we're opening in the negative direction. So we're opening horizontally and we're opening specifically to the left. Okay, so if we were to kind of sketch what this graph looks like, it's going to be a U that's opening to the left-hand side. Okay, so keep that in the back of your mind as we're identifying these attributes so we can make sure that they make sense and all the points seem to be fitting together. Now, one of the key values we need to find in relation to this particular equation is the value for p. So with ellipses, with hyperbolas, we find a, b, and c. With a parabola, we find p. So it's going to be based on this number here, -8. -8 is what we're going to call 4p. So negative 8 is 4p. That means if we divided negative 8 by 4, we can get our value of p. So negative 8 divided by 4 is going to be negative 2. So p is going to be negative 2. We're going to use that number in a variety of different ways in order to get an accurate graph. Now the next thing we want to find is going to be the vertex of this parabola. The vertex is what we kind of think of like the center of the graph. It's the starting point, and all the other points on the graph are going to emanate from this vertex. So we go back to the standard form for our equation, and we're looking for x minus h and y minus k. H and k are going to be the coordinates of our vertex. So x minus 4, the subtraction is part of the formula, so the number subtracted is 4, and that's going to be the x coordinate of the vertex. Now for the y coordinate, the standard form has y minus a number, so we're going to think of that plus 3 as subtraction of a negative 3. So that means that the coordinate here is going to be negative 3. Okay, so that's going to be the starting point for everything else we graph, so let's go ahead and put that on our coordinate plane. So 4, negative 3 is our vertex. So 4, negative 1, 2, 3. And I'm going to draw this one fairly large because it is an actual point on the graph. It's not a point of reference, it's an actual point on the graph of this parabola. Okay, the next thing we want to identify is our focus. The focus is not on the graph, it's a point of reference, but it's a very important one that's going to help us identify key points that are on the graph. So our focus is going to be based on both the vertex and our value of p. And this is a moment when we also need to go back and think about the orientation of our graph. So if we were to look at our coordinate plane, we know this is our vertex, this is our starting point. Based on the orientation we determined, everything else is going to open up to the left of this particular point. Okay, so that's going to be important. So from the vertex, the focus is always going to be inside of the parabola based on the direction in which the parabola is opening. It's opening to the left, which means the focus is going to be to the left of the vertex. So it's going to be along the same line, along the same grid line at negative 3, but it's going to be to the left of that. So how would we take something that stays at negative 3 and move it to the left? We have to change the x-coordinate. So we're adjusting the x-coordinate by whatever the value of p is. Now notice p is already negative, so subtracting versus adding, we've already taken care of the signs because p is negative. So our focus, again, we're moving to the left of our vertex. So starting at an x-coordinate of 4, we're then going to adjust by p, which is negative 2. And then we're not moving vertically, so we're going to keep the y-coordinate constant. And when we simplify that, that's going to be 2, negative 3. So our focus is going to be 2, negative 3. Now when I graph this, 2, negative 3, I'm going to graph it small because it's a point of reference. It's not actually on the graph. Okay, now the next thing we want to find is our focal diameter. You can think of that like the width of the parabola. It's going to tell us how wide the parabola is if we look at the points on the parabola that would pass through, that would connect passing through the focus. So if we were to draw a segment that passes through the focus from one side of the parabola to the next, that is what's referred to as the latus rectum. So it's going to be an axis that goes from one side of the parabola to the other, specifically passing through the focus. Now this is a really easy one to figure out because you can almost just look at the equation and see it. This 4p, this negative 8, you take its absolute value. So if it's a positive number, it's not going to change. If it's negative, it's going to flip and become positive, and that's going to be your focal diameter. So again, think of that as the width of the parabola. If you take the width passing through the focus, that's how wide, that's how many units it's going to be to get from one side of the parabola to the other. Now, I like to think of this in terms of a focal radius, if there is such a thing. So focal diameter is the whole width, focal radius would be half of the width. Focal radius would be half of 8, which is 4. Think of 4 as being the whole width that's been divided in half. So 4 represents how many units we have to go from the focus to go from one side. So we go 4 units above, we go 4 units below. So I like to think of it in terms of 4 because in some ways that's going to be a more helpful number. But if we're looking for focal diameter, it is 8. Our width is 8. So the endpoints of the latus rectum, that's what we're going to use for. We want to know what are those actual points on the graph based on them being in line with the focus. So let's think about how we would find these. Now this is kind of unique. We're no longer starting at the vertex. We're now looking at the focus as the point of reference, as the point we're adjusting. So we want to go above the focus and we want to go below the focus a certain number of units. Okay, we're holding the x coordinate constant and we're just increasing and decreasing the y coordinate of the focus. So we're starting from the focus, which is 2, -3. We're holding the x coordinate constant, and then the y coordinate is going to increase and decrease by 4, by half of 8. So we're going to add and we're going to subtract 4. And we split that up into 2 separate points. That's going to be 2 and -3 plus 4, which is 1, and 2 and -3 minus 4, which will be -7. So the endpoints of the latus rectum are 2, 1, and 2, -7. So let's put those on the graph. So 2, 1, I'm going to draw it bigger because it's an actual point on the graph, and then 2, -7. Now here's a moment to take a step back and just make sure things are making sense, make sure things seem to be reflected correctly on the graph. Number one, these points are evenly distributed away from our focus, and also if you go from one point to the other, notice it's 8 units in total. That's what we mean when we say focal diameter. Now at this point, those 3 points are sufficient to get an accurate graph. So if we want, we can go ahead and we can connect the points with a roughly U-shaped curve. Just do your best, it doesn't have to be perfect. And that is essentially going to be the graph of our parabola. Okay, now we were asked for a couple of additional things, so we'll look for those additional things before we finish up. These 2 attributes of the graph are going to be much easier to find once you've found everything else and you've already generated the graph. So the directrix is kind of like the focus in that it's not really there, but it's an important reference item. Because technically speaking, the formal definition of a parabola is that it's all the points that are equidistant from both a fixed point, the focus, and a fixed line, the directrix. The directrix is always going to be outside of the parabola. So if the focus is a certain number of units in one direction, the directrix will be the same number of units in the opposite direction. So the focus was 2 units to the left, the directrix will be 2 units to the right, and it's going to be a line. So in this case, it's going to be a vertical line. We can graph it before we even look at the numbers. So 2 units to the left versus 2 units to the right, and then just graph the vertical line that passes through that location. That will be our directrix. And then we can write the equation of that. It's a vertical line, so it's of the form x equals a constant, and the constant number it's passing through is 6. So our directrix is going to be x equals 6. Now, if we want to be a little bit more formal, how are we finding that value if maybe the numbers aren't ideal and we need to figure it out using something other than a graph? This relates back to the vertex. So if we think about what's happening with the graph, we're starting at the vertex and we're moving a certain number of points or a certain number of units to the right. So we're holding the y constant, but we're changing the x. Now the vertex is at x equals 4. So think of it as starting at x equals 4, and then rather than subtracting 2, we are adding 2. And we get to, again, x equals 6. Now, when we write the directrix, it's important that we have both the x and the 6. The directrix is a line. A line has to be represented by an equation. So if you just say the directrix is 6, that's not correct. 6 is not even a point. 6 is just a number. X equals 6 is the vertical line passing through the x-intercept 6, 0. Now the other line of reference is referred to as the axis of symmetry. It's essentially the mirror edge that passes through the vertex. So it's the line that passes through the vertex on either which side of which we have mirror images for our 2 sides of our parabola. So our vertex is here at y equals -3. So we're going to draw the horizontal line. I'll start over here. Draw the horizontal line that goes through -3. And that's another one of those values or one of those attributes that's easier to find once you actually have the graph and you can just reference the graph. Okay, So notice it didn't move in relation to any of the values, any of the points. It's just the horizontal line that passes through the vertex, so it has to have the same y value as the one associated with the vertex. So horizontal line, y equals a number, and then it passes through the vertex, which has a y coordinate of -3. So the equation is going to be y equals -3. Okay, so we have all the attributes that the system wanted. We have a pretty accurate graph. Now let's see if we can translate that into something in our homework system. Okay, so first off, we're looking for our vertex. Now we determined that our vertex was 4, -3, so let's type that in. Now don't check it yet, we need to fill in everything for this step. We also determined that P was -2. We determined that our focus was 2, -3. And then we determined that the focal diameter was 8 units. Now we can check it. Okay, all of that is correct, so we know we're operating off of correct assumptions when we were graphing. Next, we want the endpoints of the lattice rectum, so those additional 2 points that we graphed that were distributed away from the focus. So the first one was at 2, 1, and the second one was at 2, -7. Let's check that. Okay, and now we can graph. And notice we're graphing before we actually type in and identify any additional attributes. That's because those attributes aren't completely necessary in order to get an accurate graph. So just the points, just the values we have up to this point in the problem are enough to get an accurate graph. So let's click our parabola tool. Let's see what we need. So we need our vertex first, and we determined that was at 4, -3. So 4, -1, 2, 3. Place the vertex. Now, it's worth mentioning if you have a vertex that doesn't fall on your grid lines, you may have to use the point plotting tool first. So if you can't just drag and drop your vertex accurately, if that would require some approximation, then you can use the point plotting tool, type in the coordinates, and then you can drag and drop your vertex correctly. Now it tells us to choose how the curve opens. So remember, that was part of determining the orientation. We can open up, we can open down, we can open right, and in our case we open left. So we'll orient the curve the way we want, click again, and then we want to place another point that's on the graph. This is where we use the endpoints of the lattice rectum, either one, so 2, 1 or 2, -7. So if we use 2, 1, here's 2, 1, place the point, and we've got our graph. So notice we needed 3 things here. We needed the vertex, we needed the orientation, and then we needed to place another point. And one of the lattice rectum endpoints, since you've already found it, that's a good one to use. So let's check the answer. And there we go. We've got a good graph. Now, what if your graph is marked wrong? You know all the attributes up to that point are correct. More than likely, if it's marked wrong, maybe there was a fractional value that you approximated. Here we didn't have any fractional values, so that wouldn't be likely. That wouldn't be, more than likely, that would not cause a graph to be marked wrong. So if it's marked wrong, it probably means maybe your orientation was wrong, maybe you just plotted a point incorrectly. All of those are things to go back and consider if your graph is incorrect. So our last step, equation of the directrix. Again, it's an equation. It's an equation of the form x is equal to a constant, and in this case the constant was 6. And then our axis of symmetry was y is equal to -3. Okay, let's check it. And there we go. Okay, so again, as with any graphing problem, do as much of this as you can on paper in advance. Not only so you're confident graphing by hand, but so you have something to fall back on. There's a lot of little parts that go into graphing a parabola, and we make a mistake on one and it can propagate through the rest of the problem, and it can result in an incorrect graph. So make sure you do as much as you can on paper, then you have something to go back and check if you run into any problems. So that is graphing a parabola in the Connect and ALEKS system.